Hello, ladies and gentlemen. It's New York City today. I'm speaking to you from the top of some big building, and I want to talk about this is lecture 5, and we're covering section 2.5, which is called Equally Likely Outcomes. So I'm going to get started. Today, I'm going to use a different piece of technology. I'm going to use an iPad instead of the tablet I was using. I'll see how that works out. Okay, so let me begin by pulling up a whiteboard. Okay, so 2.5 is the section, and it's equally likely outcomes. Okay, so here, let's start with an example. In fact, we've sort of been doing, in the previous lecture, we kind of worked in the situation a little bit. So here's an example to think about. Suppose I have a fair die, and the sample space then is the numbers the integers from 1 to 6. Okay. And now, in the case of a fair die, the probability of getting 1 is equal to the probability of getting 2. The probability of any outcome is the same as the probability of any other outcome. That means since the numbers have to add up to 1, the sum of all the probabilities of all the outcomes has to add up to 1. That says that P of I is 1/6 for I equals 1, 2, 3, 4, 5, or 6. So that's an equally likely outcome situation. A non-example of an equally likely outcome is a so-called biased coin. So you have what the sample space is modeled by two outcomes, heads and tails, but maybe the probability of heads is not a half, maybe it's 0.6, so the probability of tails would be 0.4. So that doesn't look like much of a 4, so I'm going to make it more of a 4. Okay, so we're only interested in this section in the case of equally likely outcomes. So that means that if S is the sample space, then P of a singleton, that is an event, is given by 1 over the number of elements in the sample space, right? I'm assuming the sample space is finite for this to even make sense. Okay, so now here's an observation. If so the probability of a single outcome is 1 over the number of elements in S. If E is an event that's a subset of S, then the probability of E is given by the number of elements in E divided by the number of elements in S. And that's by axiom number 3, which says we can write E as a collection of mutually exclusive singletons. Singleton means a set with one element. And then we can sum up overall the probabilities of every singleton, every outcome. A singleton is just an outcome in E, and that's what you get. Okay, so this is the number of elements in E divided by the number of elements in S. Okay, so let me do an example. 2 dice are rolled. Let's assume they're fair dice. And when you roll 2 dice, there are 36 outcomes we saw. 1, 1, 1, 2, etc., all the way up to 6, 6. And E will be the event we sum the dice. And so we want to know if the sum of the dice is 7. That's the event. Okay, so this is the set. If you think about it in set theory language, this is the set of ordered pairs x, y, such that x plus y is equal to 7. These are integers, and 1 is less than or equal to x is less than or equal to 6. 1 is less than or equal to y is less than or equal to 6. Okay, so what are the we can also write this explicitly as we've seen this before: 1, 6, 2, 5, 3, 4, 4, 3. I forgot 5, 2, 2, 5, and 6, 1. So how many are there? There are 1, 2, 3, 4, 5, 6, 7. I'm missing something. 1, 6, 2, 5, 5, 2. Oh, I counted twice. 2, 5. That's no good. Okay. So how many outcomes are there? There are 6 outcomes. So the probability of E, according to this, is the number of elements in E, which is 6, divided by the number of elements in the sample space. But there are 36 elements in the sample space, so we get 1/6. The probability of making a 7 is 1/6. Okay, so good. And why is it 1/6? Because 6 over 36 is 1/6. Stupid. Okay, so I'm going to do an example from the text now. Let me first save this page, and then I'll clear the whiteboard. Good. Okay, so this is example 2.5.6b in the text. So what you have is a bowl with 11 balls in it, and they're colored in 2 colors. Six are white, and 5 are, the remaining ones are black. And you draw 3 balls randomly from the bowl. And we want to know what the so let E be the event that when drawing 3 balls, we want exactly 1 ball to be white and the others to be black. Okay, so here's the solution to this problem. The idea is first of all, let's figure out the cardinality of the sample space here. So the sample space are all ways of drawing 3 balls out of the urn or the bowl, right? And if we grab 3 balls out of the bowl, we're selecting 3 balls from 11 balls. So that should be 11, choose 3. So that's simple enough. Now notice any configuration, any way of drawing 3 balls randomly, if we don't pay attention to the colors, is equally likely if we ignore the colors. So this is an equally likely situation. And the thing is, we have to compute the size of E, the number of outcomes in which exactly 1 white ball is drawn. But how can we draw a white ball? Well, the only way to draw a white ball and 2 black, we have to draw 1 white ball and 2 black balls. So how many ways are there of drawing a white ball? Well, there's 6 white balls, so there's 6 choose 1 ways of drawing a white ball. And likewise, there are 5 choose 2 ways of drawing 2 black balls. Right, and if we do both of these operations, selecting a white ball and selecting 2 black balls, the number of total ways of drawing is the product. 6 choose 1 multiplied by 5, choose 2. This is the number of ways of selecting exactly one white ball and 2 black balls. Okay, so that's the size of E. That's exactly the size of E. So the probability of E is 6 choose 1 times 5 choose 2 divided by 11 choose 3. And you can compute what this is even by hand. It's not hard. I will spare us the boring details. We'll get 4/11ths as the answer. So that is the result of the calculation. The probability of E is 4/11ths. So I'm going to save the page and clear the whiteboard. So I'm going to do example. I'm jumping around here. I'm not doing all the examples in the text. I'm just doing the examples I find interesting. So this would be 2.5G. So it's about 5-card poker hands. And there's a poker hand which is a full house. Maybe I should explain. So a standard deck of cards, if you've never played cards before, has 52 cards. And there are 4 suits. There's spades, hearts, clubs, and diamonds. And each suit has 13 cards. Okay, 13 cards are in each suit. So they go ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's a jack, a queen, and a king. So that makes 13 cards. So a full house is 3 cards of a kind. Kind meaning 3 cards with the particular value, either ace or 2 or 3. There are 4 cards, by the way, of each denomination. So three cards of a denomination. So there are 4 cards. Either there's an ace of spades, an ace of hearts, an ace of clubs, an ace of diamonds. There's a 2 of spades, a 2 of hearts, a 2 of clubs, and a 2 of diamonds, and so on. All right. So a full house is 3 cards of a kind and 2 cards of a different kind. For example, you could have 3 4s and 2 jacks, and that would make a full house. And so let E be the event of getting a full house. Okay, so this is really bad handwriting. Let me clear that up. Okay. So the question is how do we compute the probability of E? And we can actually do this now. So the sample space is all 5-card hands from 52 cards, right? So how many ways of doing that are there? That's selecting 5 cards from 52 cards. So the cardinality of the sample space is 52, choose 5. And that's fine, right? So that's easy. So now we have to compute next the size of E to get the probability of E. And so how do we build a full house? We have to figure out how to build a full house. Well, in order to build a full house, we have to figure out, we have to choose a kind that is a denomination. So how many ways of doing that are there? Well, there are 13 denominations of card, 13 kinds of card, ace, 2, 3, 4, 5, all the way up to jack, queen, king. So there are 13 choose one ways of choosing a kind. And then once you've chosen that one kind, we have to choose another. That's the kind you're going to use to build the three of a kind, right? So how many ways are there to build three cards from that kind? Well, there are four cards in a denomination, so it's got to be 4 choose 3. This is the number of ways, if we multiply these two together, it's the number of ways of choosing from a deck of cards 3 cards of the same denomination, the same kind. Now, we're not done. We have to still choose our 2 of a kind. And so we have to choose another kind. Now, we've already used up one kind. So, so we have to, there are only 12 kinds left in the deck. So we have to choose another kind. And then once we choose that other kind, we have to choose 2 cards from it out of the 4 cards in that kind or in that denomination. So it's 4 choose 2. So that's what you get. And so the size of E is this product. That's what we get out of this. And so the probability of E, let me do that over here, is 13 choose 1 times 4 choose 3 times 12 choose 1 times 4 choose 2 over 52 choose 5. And this is not hard to compute with a calculator or one of these online things that compute combinations. You're going to get 0.0014. It's a pretty unlikely event. It's very small. So that's the answer to the problem. Okay, so this is going to be my last problem for today, or example for today. It looks like it's 2.5 I think. I haven't checked, but it's called the birthday example or the birthday problem. This is actually really cool. So suppose you have n people in a room. So the idea is you have a number of people in a room, like you're at a party, let's say, and you're going to ask, what is the probability that 2 people celebrate their birthday on the same day of the year? And you might think you need a lot of people for that because there are 365 days in a year, but uh, maybe you have 20 people or 25 people at the party. That doesn't seem likely. But in fact, it is very likely if you have 25 people. In fact, you'll see that it becomes very likely when you have 30 people. So here's the idea. We're going to compute the complementary thing. Let E be the event that no 2 people celebrate their birthday on the same day. Okay, so the question is, what is P of E? What's the complementary event? The complementary event is the event that at least 2 people celebrate their birthday on the same day. So let's first compute the probability of E. And I'm going to simplify, like let's pretend there are no leap years. You're not in a leap year, and nobody was born on February 29th. So this is a minor point that we should ignore. Okay, so the question is, so a year has 365 days, right? Okay, so a year has 365 days, and I want to consider the configuration. So we want to figure out what the sample space is. The sample space is an n tuple of days of the year, right? That is, you go around the room and you ask, what's your birthday? April 1st. What's your birthday? June 29th. And you list that all of those days, and you get an n tuple of days of the year. So that's right. Okay. So I'd like to. So let's. So what is? So the size of S is what? Well, every day of the year is 365 days. So how many n tuples are there? There are 365 to the power of n such elements in our sample space, because it's you have to choose a day of the year, then you have to choose another day of the year, and so on until you get through all the people in the room. Okay, now what is E? What is its size? E is the set of n tuples in which no repetitions occur, right? So let me indicate that first. E equals the set of n tuples in which no repetitions occur. Okay, so what is the size of E? What is the cardinality of E? Well, you go to the first person in the room, he or she has a birthday, so 365 choices. You go to the second person, if you want the second person not to have the same birthday as the first person, there are only 364 choices for that person's birthday. And you keep going, 363, etc., until you've exhausted the entire room, and you'll end up with 365 minus n plus 1, it turns out. You can count, you'll see you'll get n, this is a product of n different numbers. So what's the probability of E? That's this number, 365 times 364 times 363, all the way up to 365 minus n plus 1 over 365 to the nth power. By the way, it may be easier to write this as 365 factorial over 365 minus n factorial times 365 to the power of n. That's a more compact way to write it. Okay, so that's the probability, but now I want to ask the question, I want to ask two questions, because that's actually, I didn't even ask the question. I computed the probability of E, and that's the answer, but I'm going to ask a different question now. So let me save this and then clear the board. Okay. Okay. So so where are we? We know that P of E is 365 factorial divided by 365, well, minus n factorial times 365 to the power of n. So the question B is, when for which numbers n is probability of E smaller than 1/2. So you're going to have to solve an inequality for that. You have to solve the inequality is less than 1/2. And that's not so easy to solve in general, but you could actually do it by trial and error, brute force. And you'll see that if n is at least 23, then the probability of E is less than 1/2. So this is by trial and error. That's a lot of trial and error, but we can do it. It's not hard, it turns out. Now, what is the probability of E complement? E complement is the event that no two people in the room have the same day of the year, which they call their birthday. And if P of E is less than 1/2, then P of E complement is bigger than 1/2. So it's better than 50% odds. Better than 50% odds that if you have at least 23 people in the room, 2 of those people will have the same birthday. And in fact, when I teach this class live in person, usually there are 30 people in the class, and I go around the room and ask, what's your birthday? And it always is the case that 2 people share the same day of the year as their birthday. So I think that's it for today, and I hope my writing was legible on this iPad. If not, please give me some feedback. Okay.